In this video, I will briefly explain the partial fraction expansion method, and we will start by some theoretical concepts and definitions which are required to learn this topic. After that, I will briefly explain the partial fraction expansion algorithm, and later on we will see a comprehensive example which will pertain all the possible cases that can come up in this method. At the end of this video, I will do this partial fraction expansion using MATLAB. So at any point, if you want to skip to any subsection of this video, you can do that by going to bookmarks which are available in description of this video. Rational function or rational fraction can be defined as a fraction having numerator and denominator both as polynomials, and these polynomials can be of any degree and they can operate on any algebraic variable, whether it could be a real variable or a complex variable. In this example, the numerator polynomial has highest power of the variable as 2, so it is second degree polynomial, and the denominator has the highest power of the variable as 3, so it's a third degree polynomial. Proper fraction is a fraction having value less than 1, means the numerator is of lower value than the denominator. For example, here you can see in these examples. So all the resulting value of these fractions is less than 1. Proper rational fraction is a rational function having numerator polynomial of lower degree than the denominator polynomial, as we have seen in the last example. So numerator polynomial is of degree 2 and the denominator is degree 3 polynomial. Contrary to proper fraction is the improper fraction, which will always have the value greater than or equal to 1, means the numerator is of higher value than the denominator, as you can see in these examples. So all the resulting values are greater than or equal to 1. So this is called the improper fraction. So improper rational fraction is a rational function having degree of numerator polynomial greater than or equal to the degree of denominator polynomial. And for example, in these problems, we can see the first function fx has numerator polynomial of higher degree than the denominator polynomial, and g of x has both numerator and denominator polynomials of same degree. So next important concept is poles, which are the solutions or roots of the denominator polynomial in any rational function. We can find out the value of poles by equating the denominator polynomial to 0, and then solving for the variable, we will get the value of the pole. So for example, s plus 2 is the denominator polynomial, we equated it to 0, and then solving for value of s, we will get the pole value at minus 2. So for example, in this function has two poles, one at x is equal to minus 2 and other one at x is equal to minus 3. So these are the solutions of this denominator polynomial. Poles are actually singularities of a system which actually makes the function undefined. As we can see in this example that minus 2 pole value makes this function f of x as infinity, and similarly the second pole minus 3 makes this function f of x as infinity 2. So these two poles are actually making this function undefined. And the degree of denominator polynomial defines the how many number of poles are there in that function. So as we multiply these factors in the denominator, so it will become x square plus something. So x square means this polynomial is of second degree, and same way it is having two poles. So partial fraction expansion is actually the decomposition of a rational function into sum of partial fractions. So these partial fractions are basically simpler irreducible proper fractions which cannot be further subdivided. As in example of this function, we can see that this complete rational function is shown as a sum of these two irreducible proper fractions. So these proper fractions will be come up as one for each pole. So x plus 2 is having one pole, one proper fraction, and x plus 3 is having another pole, second proper fraction. So these two proper fractions are getting added up, and if we take the LCM of these partial fractions, so it will transform again back to the complete rational function. Now we will understand a comprehensive case of a partial fraction expansion. So for example, f of s is a rational proper fraction and PR is the repeated pole. So repeated pole means this can be of any nth order repeated pole. So for example, it could be s minus 1 raised to power 4. So that means this polynomial has s is equal to solution as 1, 1, 1. So 4 poles at 1. So same way it can be having another repeated pole. So at any value, for example, it is s cube. So that means s is having 3 poles at origin 0. Okay. Next is the case for pi. So pi is basically real and distinct poles. So it is a product of real and distinct poles. There can be any number of real and distinct poles which are all getting multiplied by each other, and we can see, for example, like it could be s plus 1 into s plus 2 into s plus 3. So here we can see that 3 real and distinct poles are actually getting multiplied. So this factor is basically showing the real and distinct poles all multiplied together. So poles can also be complex numbers, and when the pole is complex number, then there must exist its conjugate pair. So complex poles are always existing as conjugate pairs, and there could be any number of conjugate pairs multiplied together. So complex numbers always exist in conjugate pairs. For example, we can have s plus 1 plus 2 iota into its conjugate pair s plus 1 minus 2 iota, and another complex conjugate pair, for example, s minus 2 iota into s plus 2 iota. So like this example, the denominator polynomial can have any number of pairs of complex conjugate pairs. So partial fraction expansion of this rational function will be as shown here. So in case of repeated pole of nth order, so there will be n number of partial fractions added up together. So each partial fraction is having the factors power increasing. So starting from first power, second power, and up to nth power. So for example, if we have the highest repeated factor as s plus 1 cube, so then this will be transformed as k1 over s plus 1 first order factor plus k2 over s plus 1 square plus k3 over s plus 1 cube. So that's how we will do the partial fraction expansion for repeated root terms. So in case of x number of real and distinct poles, there will be x number of partial fractions and one partial fraction for each real and distinct pole. So if we have 3 real and distinct poles, then we will have 3 individual partial fractions, and then we will add up all the complex conjugate pairs. So for that conjugate pairs, for each complex pole, there will be a partial fraction, and next to it will be the partial fraction for its conjugate pair. So that's how we will write up all the complex conjugate pairs in the form of partial fractions here. The numerators in these partial fractions are represented as k, and they are called residues. And these residues can be numbered in any order. And these residues are the only unknown in this partial fraction expansion, and we will use residue evaluation method to find out these residues. So this residue evaluation method will work for finding out all the residues except partial fractions with repeated roots. So for repeated roots, there will be a slightly different method to find out their residues. So in any rational function, there could only exist these types of 3 poles: repeated poles, real and distinct poles, or complex conjugate poles. So we can have problems in which any one of these pole types of poles exist, or they can exist in combinations of two or combinations of three. Next, we will see a brief example in which all these three types of poles exist. So in this example, we can see that in denominator we have denominator polynomial of fifth order, and numerator polynomial is also of fifth order. So this is a rational improper fraction. So in case of improper fraction, we must have to do the polynomial division. And when we will do polynomial division, we will get direct term or a quotient plus a fraction, which is a rational proper fraction, and it is constructed of remainder divided by divisor. So here you can see the result of polynomial division. So 4 is the quotient or direct term, and this complete remainder over divisor fraction is the rational proper fraction, and we will do the partial fraction expansion of this proper fraction. In this expansion, we have defined the partial fractions for repeated roots, one fraction for each repeated term. So k1 over s plus k2 over s square up to the maximum power of the repeated term. And then we have the real and distinct root. So here is the term for only a single distinct root here, k5 over s plus 1. Then in purple we have quadratic equation, and this quadratic equation gives rise to complex conjugate pair. So we have the poles as complex conjugate pairs, and the residues of this complex conjugate pair is also a complex conjugate pair in itself. So K3 is basically complex conjugate of K4, and K4 is the complex conjugate of K3. So if the poles are complex conjugate, then their residues are also complex conjugate of each other. So these partial fractions and their residues can be written and computed at any order. To find out K5 residue, we will multiply its denominator polynomial s plus 1 at both sides of this partial fraction expansion like this. And this s plus 1 will be multiplied by each partial fraction here. And next step, we will see about possible cancellations of these factors from numerator and denominator. Like here we can see that these cancellations can be done. After this due cancellation, we will be left with this reduced equation. In next step, we have to find out the pole of this k5 fraction, which is s is equal to -1, and then we have to evaluate this complete equation at this pole value. So this complete equation will take on the value of s is equal to -1 like shown here. And on the right hand side, you will observe that all residues become 0 except k5. We have got the more simplified form of this equation, and we will manipulate it in order to get the value of k5, which is -0.1. So now the partial fraction expansion has become like this, in which we have put the value of k5. Next, for k3 and k4 fractions, we know that their poles are complex conjugate of each other, and so their residues are also complex conjugate of each other. And these are the pole values. So we have to find out either one of these k3 or k4 by residue evaluation method. So in order to find out k3, we just have to multiply its denominator polynomial with both sides of this partial fraction expansion as shown here, and polynomial will be multiplied by each of the partial fraction like this way. And then we will look out for any possible cancellations of the factors from numerator and denominator, and resulted will be this equation, which is a further simplified equation. And now we have to evaluate this equation at the pole value which is s is equal to minus 2 plus 3 iota. This will be the form of partial fraction expansion when evaluated at pole value. On right hand side, all the residues will become 0 except k3, and equation will be further simplified in terms of k3. And if we further manipulate this equation, then k3 turns out to be minus 9.8 plus 1.25 iota, a complex number in rectangular form. And we can also write this complex number in polar form, where 9.8 is its modulus and e raised to power iota theta. 172.7 degree is its argument as theta, and also we can write it in this notation. Once K3 is known, K4 is also known, which is complex conjugate of K3, and it turns out to be minus 9.8 minus 1.25 iota. Now this is the current state of partial fraction expansion, and only unknowns left are the K1 and K2. So in case of repeated root terms, the residue evaluation method only works for highest ordered factor, which is s square here. So we can find out K2 by this method here. So we just have to multiply the s square at both sides of this partial fraction expansion, and it will be turned out like this. And then we will see about the possible cancellations of a s square factor from numerator and denominator. And the resultant equation will be like this, and I have termed this equation as equation A. So this equation A is important, as this equation A will be used further to find out the subsequent residues of lower order factors. For example, K1 here in this example we have only lower order factor is K1. So for K2 I just have to evaluate equation A at repeated pole value, which is s is equal to 0. Upon evaluation, on left hand side only K2 will be left, and all other residues will become 0, and this equation will be simplified in the form of K2 as this, and we subsequently get the value of K2 as 0.23. So this will be the resultant equation of partial fraction expansion. So for residue K1 we have to differentiate equation A with respect to s, and the resultant will be evaluated at repeated pole value s is equal to 0. So when this derivative is distributed over partial fractions, so the resultant will be this equation. Now we have to find out the left hand side of this differential equation. So in this we will find out the derivative of this rational function. So derivative of rational function involves the quotient rule, and the quotient rule is defined as this relationship, where ns is the numerator polynomial and ds is the denominator polynomial. So according to quotient rule, the resultant will be denominator as square of this denominator polynomial, and in numerator denominator polynomial into derivative of numerator polynomial minus numerator polynomial into derivative of denominator polynomial. So according to quotient rule, we will now solve this differential. So this derivative will become equal to this equation. So when we have applied the quotient rule on this rational function, so we will further get these two differential equations. So one is the derivative of this numerator polynomial, and other one is the derivative of this denominator polynomial. In order to complete the evaluation of quotient rule, we also have to find out these derivatives. So in this part we have to take derivative of two multiplying polynomials, and multiplying polynomials derivative involves product rule. So we will obtain this derivative using product rule, which is very simple, and it is stated here. So product rule is basically first function multiplied by the derivative of second function plus the derivative of first function into the second function. And finally we will get this final polynomial, which is the derivative of this multiplying polynomial rule. In next step, we have to take the derivative of this polynomial, which will give us a resultant polynomial. Now we have to replace these both derivatives with their respective resulting polynomials. So these two derivatives will be replaced by their results, and finally we will get this equation at the left hand side of this overall derivative equation. Now the derivative of equation A is being transformed into this final equation, in which at the left hand side you can see the derivative of rational function like this form. And now we will compute the derivatives at right hand side. So here the derivatives of repeated root terms residues is very simple, which is k1 plus 0. Next are the derivatives of other residues, which will be taken as quotient rule. So, for example, I just have taken one derivative here. So, other derivatives will be the same using quotient rule. So, as we have seen previously, that the only required residue will remain there, and all other residues become 0 when we evaluate this function at repeated pole value. So, same will be the case for valuation of k1. So when we will evaluate this complete equation for k1 at a repeated pole value s is equal to 0, so then these terms will become eventually 0, which are based upon other residues. Now when we evaluate this complete equation at repeated pole value s is equal to 0, so then this will be the resultant. And here you can see that at right hand side, other than k1, all other terms will become eventually 0. So that's why we don't need to calculate them and don't need to do extra computation. So after evaluation at repeated pole value, k1 equation will become very simple, and we will further manipulate this relationship in order to get the value of k1, which is minus 0.3. So the complete partial fraction expansion of this rational proper fraction is shown as here. So in which we have find out all the residues from k1 to k5. So once the partial fraction expansion is complete, then this overall rational function can be transformed into the following phases. So here you can see that how this improper function is represented in terms of direct term and summation of all the partial fractions. So this overall time taking and complicated process can be done very easily using MATLAB. So in MATLAB, we first have to define our rational function in terms of coefficients vector. So we have to find out all the coefficients of numerator and denominator polynomial, and we will define the row vectors based upon these coefficients as shown here. So these numerator and denominator coefficient vectors can be defined in MATLAB environment using following commands. So polynomial multiplication can be done in MATLAB using command conv. So conv is basically convolution or polynomial multiplication, which operates upon two coefficient vectors. So we have to give them coefficient vectors of the multiplying polynomials, and it will give us a single polynomial in resultant. So for example, we have to multiply these polynomials in order to get this complete polynomial. So we will use this command in MATLAB as follows. So first we will convolve or multiply these first two polynomials and will get a p1 polynomial, and then at second step we will again multiply this p1 polynomial with the third polynomial, and the final polynomial, the denominator polynomial, will be obtained. So we have got this same polynomial in the result. If roots of the polynomial are known, then polynomial coefficient vector can be obtained using command poly. So poly command is used to convert roots to polynomial, which operates upon the roots vector. So we have to give the vector of roots to this command, and it will give us the polynomial coefficient vector. So for the same example, we know the roots or poles in this specific case. So we have a pole of order 2 at 0 and -1 and two complex conjugate poles. So if we give this poles to the poly command, then it will give us these coefficients of this complete polynomial. So MATLAB command and syntax would be like this. So by using this command, we have got the same coefficient vector. Once coefficient vectors of numerator and denominator polynomials are known, so then we can find out the rational function by using the command tf. So tf is to construct or to convert to transfer function. So tf will convert these coefficient vectors into a continuous time domain transfer function, and it will be shown like this. So in MATLAB command, we have to give the coefficient vectors to the tf command like this. So these complete transfer function, rational function form can be verified in MATLAB environment. Once coefficient vectors of numerator and denominator polynomials are known, so then rational function can be converted into partial fractions using command residue. So residue is basically partial fraction expansion, and it results into residues, poles, and direct terms. So MATLAB command for this process will be residue, and input arguments will be numerator and denominator polynomials, while output arguments are RPK, where RPK are the corresponding vectors of residues, poles, and direct term K respectively. So this overall partial fraction expansion, the residues, the poles, and direct term can be verified in the result of MATLAB. So the direct term K is equal to 4. So respective conjugate poles, complex conjugate poles have respective complex conjugate residues in order. So the pole -1 has residue -0.1, and repeated poles at origin has respective residues as -0.3 and 0.23. So that's how we can do partial fraction expansion for any rational function very easily in MATLAB by using this command residue. I hope this video is helpful for you in learning the method of partial fraction expansion and learning to do it very conveniently using MATLAB. Thanks for watching.